Good evening. This is Boaz Adelberg, and the topic of our discussion today will be the Jacobian Matrix. We will take a look at different applications of the Jacobian Matrix in robotics. We look at its definition, and also we look at an example. We will use Jacobian Matrix in precision analysis of robots, inverse kinematics, and force and stiffness analysis. The definition of the Jacobian matrix, assuming we have a function, vector function f, as a function of independent variables x, then the Jacobian matrix is a matrix that each one of these components represent the partial derivative of a given function I, the Jacobian element at row I and column j is the partial derivative of function I with respect to the independent variable j. Now let's take a look at an example in our robotic field. If we are given, for example, a vector function of xi as a function of independent variable theta I, for example, in this two-link robot, we have theta 1 and theta 2 as the angular position, relative position of each one of the link with respect to each other, and we have x and y, the position of the two center point, in a coordinate system x0, y0, then we can write an expression of xy as a function of theta 1 and theta 2. And we see that expression here. X, as you can see here, is equal to r1 times cosine theta 1 plus r2 times cosine theta 1 plus theta 2. It's a little difficult to see that, but the angle is the angle between this horizontal line and the link line, and it is the sum of the two. It'll be easier if you extend this link beyond this line, and then it'll become very obvious. The y component, as we see here, is equal to r1 times the sine of theta 1 plus r2 times the sine of theta 1 plus theta 2. And this is what's actually written right here as an expression. The Jacobian matrix, according to the definition that we saw, will be taken as the first element, the partial derivative of x with respect to theta 1. But theta 1 shows here in the two elements, so it will be minus r1 sine theta 1. Sine is the minus sine is the derivative of cosine, minus r2 sine theta 1 plus theta 2. Now the second term, which is the partial derivative of x with respect to theta 2, since theta 2 does not show up here, will only be minus r2 sine of theta 1 plus theta 2. And similarly, we can find the other terms of the Jacobian. Now, we are having in robotics a problem which is called inverse robotics kinematic, or IK, and a forward kinematic problem. Now, the forward kinematics determines x as a function of theta, as we saw earlier, x as a function of theta. Now, the inverse kinematics problem is more difficult one, and that is to find theta as a function of x. Now, from this expression, you see that we have to invert this vector matrix, which is not that easy, to solve for theta. Now, from the definition of the Jacobian matrix, we know that J is equal to d theta, dx d theta, which was expanded in partial derivatives. And from here, we can solve for dx as J times d theta. Now, the in order to find d theta as a function of dx, we have to invert the Jacobian matrix, and then, as you see from this expression, then we'll have d theta equals to the inverse of the Jacobian times dx. But the inverse of the Jacobian is difficult to find, and we can use an approximation for it as the transpose of j theta, which is easier to determine. Now, to find the inverse kinematic problem, we recall that x is a function of theta. It's a given function of theta. And d theta was the function, we take the transpose of the Jacobian matrix and multiply times dx. Then the iterative process starts by making an initial guess of what is theta for a known x. And then we find out what is the initial related x0 from this expression. We substitute the initial guess here, and we find the initial x from equation 1. Once we have that, we calculate the difference, delta x, between the initial guess and the desired target x. This is called delta x, and then we can calculate delta theta from expression 3. We plug in delta x here, hit it with the transpose of the Jacobian, and get delta theta. Then we can increment theta with delta theta to find a new theta, and substitute again in equation 1 to find a new x. And we repeat this process until delta x becomes less than a certain conversion factor. Now, this iterative process has many variations. I personally use one variation in my doctorate dissertation called Newton-Raphson, very effective convergence factor. This convergence system is a little bit less complex and also slower, and may have issues of convergence. Now, the convergence, the algorithm is based on Taylor's series, which takes any function and says that any function can be approximated as any point plus increment to that point, delta. Now, that whole function can be approximated by the function itself at that point plus the derivative of that function at that point with respect to all these vectors. So this is like a gradient, and multiplied times the delta x. And then there is all the other terms of the Taylor series come here as a residual, and the idea is to minimize this residual in the convergence system. So with that said, we like to conclude our presentation of the Jacobian matrix, and in upcoming presentation we'll discuss how we use it to find out the precision of a robot as well as the force and stiffness analysis that robot may be encountered with. Thank you very much for you listening, and until next time, have a good day.